Hello and welcome to my channel again. So today's topic will be Maxwell's stress tensor using proper tensor method, because I have seen on YouTube that there are plenty of videos regarding Maxwell's stress tensor, but they have used the pointing vectors method and they have used the vector method. But I'm thinking to use the most generalized method that is used in the Jackson, and I will use proper tensorial notation. So the student must know the Lagrangian of an electromagnetic field and the tensor notation, how to use the tensors and all the derivatives regarding tensor and how the tensor transformation works. So yeah, so let me just get started with the video. Okay, so as you can see, I've cleared the board, and now just let me start with the initial facts. Now we basically know that the Lagrangian of an electromagnetic field is given as you can use the Greek indices according to your choices, but I prefer mu. Now the point is, this is already known to us. If you don't know this, I will give the corresponding videos link to the I tab button. You can just go and see that. I've already done it. So regarding this Lagrangian, there will be a conserved current. Okay, also called the Noether's current. So this Noether's current will have two parts. This Noether current will have two parts. One will be due to the variation of field, that means a mu, and the second will be due to the variation of x mu. Okay, there will be two parts. If you see the I-tapped video, you will get these two things. Okay, so I will claim that this quantity or this expression T mu nu is basically Maxwell's stress tensor. Okay. And that can be written as minus eta mu nu, the Lagrangian. I'm writing a EM. If you see the I-tapped video, you will get the reference from there. And then plus I think this is okay with you guys. If I forget here the EM subscript, please assume that there is a EM. Okay. You can also write a EM here, because this is Maxwell's stress tensor just for electromagnetic fields. The field can be anything like a complex scalar field, a real scalar field, and according to them, this expression will remain same, but the significance of this or the nomenclature of these things will change. Okay. So let us say this is equation 1 and this is equation 2. Okay. Now we will ask the following question. I will ask the following question. 1. Is this quantity conserved? Because if we start from the rock bottom, then basically we have no idea what the hell this thing is. So if we apply some kinds of conservation and we label, then we can see that is it related to some kind of physical quantity or not. If it is conserved, then otherwise we have to go another way around to see what this thing means actually. 2. If it's not conserved, then what? This is the next question. If it is not conserved, then what? Can I make it conserved? So by performing some kind of mathematical jugglery, can I prove that this thing will remain conserved? This is the third question. And the fourth thing will be, how the stress tensor will evolve / transform not according to, sorry, for this maths. So how the stress tensor will evolve or transform for this third question's maths. This is our fourth question. And we can also ask the fifth question that, okay, we will introduce the fifth question later. So I think till now we have cleared our vision that what is our goal, okay, what is our need. Fine. So I will just write the inhomogeneous Maxwell's equation now. So if you guys know, then fine. If not, then you guys can just see. Okay. So F mu nu is the Maxwell's tensor. J nu is the current. I think you guys already know this. We will use this thing. And if we have no current in our system, then the J nu will be 0. So we will just have del mu F mu nu equals to 0. We will use this fact. So I will just answer the first question. Is it conserved? Okay. So we have seen that P mu nu is basically equals to this minus eta mu nu and LEM plus del LEM del of del mu a sigma del nu a sigma. Okay. Now again we can move. I want to take the derivative on both sides, because if something is conserved, then the derivative of that thing should give us a 0, and we will exploit that thing. I'll just keep my LEM as LEM plus del mu del LEM del of del mu a sigma del nu a sigma plus, this is just normal addition, derivative addition law. Okay, I think you guys are comfortable. Now this is just a contraction, so it will give us del nu LEM. Okay, and this point to be noted, this is basically the Euler-Lagrange equation, a part of Euler-Lagrange equation. So this can be written as Okay, because Euler-Lagrange equation is del mu del L del mu A sigma minus del L del A sigma equals to 0. Okay, I think you guys remember Euler-Lagrange equation. Fine. Then del nu A sigma plus. Now this is two differential operator. Okay, so it does not matter that if you write d2 dx dy or d2 dy dx. Okay, derivatives are exchangeable, so basically the derivative operator commutes in better terms. Basically the derivative operator commutes, so as they commute we can write that del L em. Please write the em if I miss somewhere. We are talking about em field. Del mu A sigma del mu A sigma. Okay, del mu A sigma. Now if you see this thing, this is basically derivative of LEM with respect to del nu, but our electromagnetic field has this Lagrangian LEM, and this LEM is a function of A sigma del mu A sigma. So basically when we are expanding in terms of total derivative, I will get this thing. If you expand this del LEM del A sigma del A sigma del mu. Okay, so this is basically total derivative. So this can be written as del nu LEM, and they basically cancel out. I will left with a 0. So from here we can prove that indeed that P mu nu quantity is a conserved quantity. So what can I write? That del mu P mu nu is equals to 0. Now let me expand the contracted or the summed index. I can expand them into spatial index and temporal index. So del 0 P 0 nu plus del I P I nu is equals to 0. Sum of two things 0. This can be written as del 0 P 0 nu is equals to minus of del I P I nu. Okay, but here we can see that these two are equal and opposite. Until or unless we know that T mu nu is basically minus of T nu nu. So our Maxwell stress tensor is basically antisymmetric. So this is not actually true. So if I change the index to nu I, this minus thing goes out of the window. So basically I cannot say that del 0 T 0 nu and del I T nu I are basically same. Sorry, T I nu are same and equal and opposite, so they basically gets cancelled out. This is not an option right now. So they individually have to be 0. Okay, so you can compare this thing with some kind of linear independence, but they are not. But you can use that analogy to understand that these two things individually 0. Okay, I don't know if the board is visible till that part, but I have written a 0 there. So due to the antisymmetric property of this T mu nu thing, we can say that this del 0 P 0 nu is equals to del I T nu I is equals to 0. So it does not matter that I write nu I or I nu with a minus, because both of them are 0. Now let us integrate on both sides. integrate on both sides. Del 0 integration T0 nu d3x. Okay, that is equals to 0 according to this. Okay, and another consideration is that del I T I nu is equals to 0 integrated over this d3x equals to 0. Now let us define P nu. Okay, define P nu equal to integration T0 nu d3x. This P nu is not ordinary momentum. This P nu is basically field momentum. So P nu is the quantity that is referring to the amount of momentum that is being carried away by the electromagnetic field. Okay, I think you remember the thing pointing vector. Pointing vector denotes that how much of energy is getting transferred through a surface. So this P nu is the same thing, but here instead of energy we're talking about momentum. So this P nu is field momentum. So I can write that del 0 P nu is equals to 0. Similarly, if we notice this part, this del I is equivalent to the gradient operator. Okay, and here we have a volume element. So gradient of something with volume integration, I can write as a closed surface integral T I nu ds nu. Sorry, the eyes are contracted. Extremely sorry. Yes. Gauss divergence theorem. And this is equals to 0. And we have to remember that as this surface has an index, Greek index, so this is not ordinary surface but a 4-dimensional hypersurface. Okay, 4-dimensional hypersurface. And this is just a single component we are talking about. It has 4 components because nu equal to 0, 1, 2 and 3. So from here we can say, so this equation represents, wait a minute, this first equation del 0 P nu represents the conservation of field momentum. The second equation represents the conservation of energy. Okay, so apparently I think you guys will assume that okay, P mu is a tensor quantity. We have defined it as stress tensor, and we have finally performed all of these calculations just to prove that the momentum carried away from the field and the energy that is being carried away by the field, both things are conserved and our job is done. But the problem is we have 3 conserved quantities: linear momentum, angular momentum and the energy. But here only I've got 2. What about the angular momentum thing? We haven't got the analogy of angular momentum from here. So what is the thing we are missing? This is the problem. So I asked you the second question, that our first goal is achieved, done, but partially, because we are missing a single thing, that is the angular momentum. What about angular momentum? So in the second question I have asked, if it is conserved Then if it is not conserved, then what? So we are missing angular momentum. This is the answer. We are missing it. And is there any way that we can play some kind of mathematical trick to show that angular momentum is hidden in this theory? Okay, so let me just rub the board and come with the angular momentum thing. Okay, so I've erased the board, and now we will talk about angular momentum. Angular momentum. So if you see that there is no analogy regarding the angular momentum, so we just have to introduce it by our own hand. So let us assume that angular momentum is conserved. Okay, let us assume that the angular momentum is conserved. Fine. This is our assumption. I am putting a star here because you guys should remember that this is the assumption. This is a claim we are taking. Okay, so we are just starting from a statement, and we will see under what consequences this statement is correct. Okay, we are trying to find the consequences, and the consequences will arrive in terms of our stress tensor. Okay, so classically, as it's a classical theory, angular momentum L is basically R cross P. We know that. So in terms of Levi-Civita notation, we can write that epsilon ijk xj pk. I think you guys will agree with this. Okay. So this is basically epsilon ijk pk. Now what? Now let us assume that L is equal to some kind of thing mi d3x. Okay. Now this is Li. That's why I taken the mi. If you want to write it like this, the point is, you guys can ask, what is the reason for writing the L in terms of a density? Okay, density integration. Because from the previous experience, we can see that our momentum, field momentum, and the energy has arisen in terms of some kind of a density. So we will, I think it is very trivial that the angular momentum, if arises from our theory, will have some kind of a density thing, angular momentum density. So we will assume that this mi is angular momentum density. This is the only expression, or this is the only explanation I have regarding this expression. And this can be written as epsilon ijk xj. Now what is pk? Pk is basically integration. P is basically field momentum here. Okay. Pk can be written as, sorry, P0k d3x. Okay. I think I'm writing it right. K to K, J to J, and I. Yes. So if I compare both sides, I will end up with mi, that is equals to epsilon ijk xj and T0k. And here it does not matter, as we are talking about Latin indices. This AI, BI and AI, BI are basically the same thing. This is just for my convenience. I'm writing on the superscript. If you want, you can write in the subscript. It's completely your choice. Okay. So now, if we want to conserve it, we should take the derivative of angular momentum, right? del 0 Li. So this will end up to del 0 epsilon ijk. Now here I will introduce the expression, that is m0 jk. I am writing what is m0 jk and d3x. Okay, so this Li, if I write it more specific, is basically mi d3x. Okay, and what is mi d3x, or specifically what is mi? Mi is basically epsilon ijk xj t0k. Now what happens if we exchange this? Xk. Okay, now not here. Xj t0k. It should be a plus, because if I have some quantity a, then I can write a plus a by 2. This same thing. It does not change anything. But due to the exchange, this t is a antisymmetric thing, will pick up a minus sign. So due to that I have a minus and xk t0j. Okay, and I will say this thing to be m0jk. Okay, this is just mathematical jugglery, and this jugglery will provide us the physical consequences or physical condition. Okay, yes, so we were claiming that this thing will be 0. Yes, due to this conservation we have claimed, otherwise it won't, but we have claimed this thing to be 0. Now if we take a sum, this is just the zeros component we are talking about. Now if we take the sum, just for all of the indices, so 0, 1, 2, 3, they don't exist because they are 0, but you can take them. This is del alpha epsilon ijk m alpha jk d3x. Okay, and this is equals to 0. Now this thing will only be 0 when del alpha contracted or performing over this element will give us 0. So the equation reduces to del alpha m alpha jk is equals to 0. Oh, sorry, I'm making a mistake again. That if I am replacing this 0 with alpha, so jk will not be here. I have to write beta and gamma. I'm extremely sorry about that, because if it is alpha, then it is the Greek index, and Greek and Latin cannot sit together. So del alpha, what is m alpha beta gamma? Just replace this index with zeros with alpha and j with beta and k with gamma. Okay, so I have xj first, so this is basically x beta. But now here the thing, as x is my position coordinate and we are now talking about 4 vector, so it will rise up and it will be something like this. Okay, because when we are talking about 4 vector, yes, when we are talking about 4 vector, it should be written on the uppercase. xj t, 0 will be replaced by alpha and k will be gamma, minus x nu t alpha beta. Yes, now I will just perform the derivative. This is the product rule of derivative. So del alpha x beta t alpha nu plus del alpha t alpha nu x beta. Okay, we can exchange them because they commute. The commutation here matters. We're not talking about quantum mechanics, but still it matters because we're talking about matrices. Matrices, not necessarily AB equals to BA. So del alpha x mu T alpha beta minus del alpha T alpha beta x. Now from the previous derivation we remember the fact that these quantities are indeed zero because T alpha beta or T mu is a conserved quantity and these indices are exactly contracted. So this will give us 0. And what is basically del alpha if I write here just for your convenience? What is del alpha? Del alpha is basically del of del x alpha, right? Oh, sorry. Alpha is down, so yeah, alpha will be up. Yes. So this is basically del x beta by del x alpha. So it will just give us ordinary Kronecker delta. So delta of alpha beta T alpha nu minus del alpha delta of alpha nu T alpha beta, and that is also equals to 0 according to our claim. Okay. So this Kronecker delta will act upon this T and we will get T beta nu minus T nu beta is equal to 0 and T nu beta is equal to T beta nu. This is a very surprising thing. Very surprising thing that the angular momentum only allowed to conserve when we take our quantity T to be a symmetric quantity. But we have already defined or we have already got the results that T mu nu cannot be a symmetric quantity. It has to be antisymmetric. So here we see a contradiction of our theories or contradictions of our understanding and what we are supposed to do about this thing, because this derivation has nothing wrong in it. The previous thing has nothing wrong in it, but they are contradictory and both of them should hold for our theory to be a physical theory. Now the problem is we don't have any answer what to do. Is it really we don't have any answer? Let's just find out by wiping the board. Okay, so I have wiped the board and we have got the answer of our third question, that can I make it conserved? Yes, under certain circumstances when our T mu nu is equals to T nu mu, that means if my T mu nu becomes a conserved quantity, then we can claim that our angular momentum will remain conserved. But we have seen on our first derivation that T mu nu is a antisymmetric quantity and that basically contradicts with our theory. The contradiction is that both linear and angular momentum and energy also should remain conserved for our theory, but the theory suggests us a contradictory statement or contradictory result from two different derivations, and here we have stuck. Now I will try to perform a mathematical calculation and we will try to see that can I have a symmetric stress tensor derived from this expression. I will try. Okay, so let us start. We know that our T mu nu is minus of eta mu nu and L, definitely with the EM, and plus del L del of del mu a sigma del mu a sigma. Okay, we have seen already this thing, but here we will do some changes first. The first change will be we will perform this explicit calculation. So our L is basically minus 1 by 4 pi I don't think I have a pi here because we are not in the Lorentz Heaviside system. I think this is just normal 4. Okay, I'm extremely sorry. This is normal 4. Okay, minus 1 by 4 if mu. I mean, it is very confusing for me also sometimes because in different units, the Lagrangian, sometimes it has 1 by 4, sometimes it is 1 by 4 pi, sometimes it is 1 by 16 pi, based on the system or based on the unit we are in. But certainly I will not take any pi is there. If I take del of del mu a sigma, okay. Sorry, I can't use the mu also. So I think sigma and rho. Okay, sigma and rho is fine. I think I should write it in a bigger manner. Del L, del of del rho a sigma. Okay, because this 2 index is already used, so I cannot use the same index thrice. Sorry, 1 by 4. This if mu I will try to open. So del mu a nu minus del mu a nu, and f mu will be kept alike. Now if you see here, this minus 1 by 4 will get outside, and this will act on this, and it will provide us delta of, okay, let me write del mu a nu but here I will perform a trick. We know that a mu b mu is basically a mu b mu. It does not matter in which manner I write this contracted index. So I will just write this mu nu and mu nu. Okay, so it is not necessary to write the second derivative part. I think you guys are already familiar with this thing. If you see the I-tabbed video I was talking about when we are talking about this part. So basically this whole thing will reduce to minus f rho and sigma. Okay, minus rho sigma. So I will just put this value up there, but here instead of rho I have mu, so I will just write minus of eta mu nu LEM, the minus f mu sigma del mu a sigma. So mu nu, mu nu, mu nu. The index are matching, so we have done nothing wrong. Okay. So minus LEM with minus f mu sigma. If I try to bring this mu down from superscript to subscript, I have to introduce a eta. That eta should be like del alpha A sigma. So here it should be alpha and it should be mu. Okay. Now minus eta mu nu LEM minus F mu sigma eta mu alpha del alpha A sigma minus of del sigma A alpha. Okay. So this is minus minus plus. So to compensate, I have to minus of F mu sigma eta mu alpha del sigma A alpha. Okay, so entire thing is balanced. In several exams, they ask to prove you these following properties, but instead of doing a rigorous derivation, I have presented the whole thing in form of a like question answer session where I have asked several questions and I will try to answer them all. But these are proper derivations. If they ask you sometimes to prove that T mu nu can be shown in some kind of symmetric matrix, this is the proper derivation we are doing. Okay, but when we are talking about derivation, we missed out a little bit of physics. So for that reason, we are talking in the manner of a question answer. So this is basically our definition of F alpha sigma. So F mu sigma eta mu alpha. Instead of writing alpha sigma, I will write sigma alpha. Please note this. I am putting a star and I will make this a plus sign because F mu nu is a antisymmetric thing, we know. And I have minus of F mu sigma eta nu alpha del sigma A alpha. Okay, fine. Now F mu sigma eta nu alpha F sigma alpha, these things can be exchanged because they are commuting. So I will just write them alongside. F sigma alpha eta nu alpha minus eta mu nu LEM. This is the thing, and rest is F mu sigma eta nu alpha del sigma A. Sometimes my sigma look alike with alpha, they look similar, but please, if you perform the calculation on with your hand on your own, then I think you will not have any confusion. Yes, so let us consider, let this minus F mu sigma eta nu alpha del sigma A alpha is equals to T0 alpha alpha contracted sigma sigma contracted, have mu nu, so mu nu. Okay, so on the basis of index we are going in right direction. So we have assumed this, let this thing is the quantity. Now we know for source free system del mu F mu nu is equal to 0 because we don't have a non-zero J nu on that side. Basically, for that reason, this is homogeneous Maxwell's equation. So now our entire calculation after this line will be performed for source free system because it is easy to do such thing. Okay, otherwise you have to perform a lot of more tensorial thing which is difficult, and people don't ask you to do such thing, they just ask you to do this. Okay, in the case of derivation also, but we can take a source in different manner introducing in a different manner, and we can still perform our calculation and get the actual result, right? So for free sources, this is the expression. So instead of using mu and nu index, we will use a different index. Sigma and mu. Sigma and mu. Fine. Yes. So if I have to exchange this sigma and mu, so these minus signs will get absorbed, and nu alpha del sigma a alpha plus del sigma f sigma mu eta mu alpha del sigma a alpha. This thing is 0 according to this condition. If you want to write this in this index notation, you can also have this. It does not matter because the contracted index does not matter. Okay, this is dummy index and this is variable index. So both of them can be treated as dummy. Fine. So you can see the derivative is acting first on this and second on this. This is a constant, so it will have no contribution. This can be written as total derivative. Sorry. So my T0 mu nu is a total derivative. Okay. But when? Okay, let us not go in this way. I will try to do the thing in different manner. So my T mu nu has reduced to this term and this term. Okay. So let us take the derivative. And we know this thing is 0 because T mu nu itself is a conserved quantity. So del mu del sigma f sigma mu eta mu alpha a alpha. Okay. Then with a plus sign, del mu f mu sigma f sigma alpha eta nu alpha minus eta mu nu. Okay, I think you guys agree. Now here the point to be noted, or the important point is, this is a symmetric quantity because they commute, and this is an anti-symmetric quantity, right? If I put the sigma and mu, if I exchange sigma and mu, this is basically same, but if I exchange them, it will become a minus sign. So basically this is a product of symmetric and anti-symmetric tensor, and we know that for the symmetric anti-symmetric tensor multiplication, this is 0, always 0. So we are seeing that del mu T mu nu, this is anti-symmetric, this is anti-symmetric, so this is a symmetric thing. This LEM also have some kind of index, induced index, say alpha beta, so this is also a symmetric thing because anti-symmetric and anti-symmetric will give you a symmetric thing. So this whole thing is symmetric, and mu is definitely a singular thing, so it has nothing to do with exchange. But so we can say that this whole thing is a symmetric thing. Thing slash quantity. Okay. So our del mu T mu nu has reduced to a form that is del mu, which is defined as theta mu nu. Okay, and we know that my del mu t mu nu is equals to 0. So del mu t mu nu is equals to 0, we know. So we can finally write that del mu theta mu nu is also equals to 0. And theta mu nu is a symmetric tensor and defined as if mu sigma alpha eta mu alpha, okay, minus eta mu L. So this is symmetric Maxwell stress tensor. Symmetric Maxwell stress tensor. Fine. And now if I want to introduce, okay, listen carefully, if I want to introduce a source term, I will do nothing. I will just take this thing, we have f mu nu, and I will explicitly try to show by introducing the del mu here. I will keep the del mu inside. Okay, I will keep the del mu inside, and I will use the, instead of using the homogeneous system, I will use the non-homogeneous Maxwell's equation. I think I will make a video regarding this thing also in form of a derivation, but not today because I think this is a complete set we are talking about. Now the physics underlying this, all of this derivation is, when we are talking about antisymmetric T mu nu, we were basically missing a particular gauge freedom. Okay, this entire theory, this entire electromagnetic theory is a theory that has certain amount of gauge freedom. Okay, we have gauge symmetry here because a mu can be transformed as a mu plus del mu, some scalar. So due to this gauge freedom, if we want to find the corresponding Hamiltonian for this theory, we have to choose a particular gauge, okay, particular gauge choice to find the Hamiltonian. So this is basically singular Lagrangian, and due to this singular Lagrangian, what happens that when we are not talking about this thing, I mean when we are not taking our angular momentum to be conserved, it will not come out from our theory because the particular gauge choice has been the particular gauge choice has not been performed. Okay, so gauge choice is important, otherwise we will not get this idea. For this particular gauge choice, we have achieved this freedom, gauge freedom, that no, T mu nu is not antisymmetric but symmetric. Okay, I think my next video will be about this thing, where I will add a source term and I will rigorously show that those videos that have derived this, all of this using the vector notation, they have used E, B or H stuff like that. I will tend to this E and B using this theta mu nu, because now T mu nu is not relevant for our theory, theta mu nu is our relevant theory. Okay, I think you have enjoyed the video. I mean, I have learned something from it. So if you like this video, please hit the like button and subscribe and comment and share.